polar world. Does anybody have any questions first on the homework problem? What we're going to do today is talk a little bit about polar graphing. Okay? I think in order for you to understand the calculus of polar curves, you really need to understand how polar graphing works. Like, it's one thing to just graph some of these things and like, oh, look, that makes a pretty flower. Oh, it makes a butt. Or, oh, it makes a heart shape. I mean, like, but understanding how graphing actually works and how polar equations sort of operate when we graph them, that will help with the calculus overall. Okay? Yeah.
I don't really understand when you have a negative R, like, does that say what quadrant it goes in? So, like,
Yes.
so so you know how we have to do a problem, so it give us, like, a point, and then you have to graph it on a thing?
Yeah.
Okay, so if it was, like, -2, 5 pi radical 3, I know where 5 pi radical 3 is, but that's in, like, the...
Wait, say what you just said again. -2 what?
5 pi over 3.
Okay.
I'm saying radical, I don't know.
Yeah, I know that's right. I didn't even hear it the first time, and then the second time you said it, I was like, wait, you said that?
Yeah. So that's in the fourth quadrant, but since it's -2, is it not in the fourth quadrant?
So 5 pi over 3 is in what quadrant? The fourth. Okay? If your angle is in the fourth quadrant, but your R is negative, that means the point that we're describing is in the opposite quadrant. So that would be in the second. So 5 pi over 3 you said is in the fourth, which I agree with. Okay? So 5 pi over 3 is there, right? But you said it was -2, 5 pi over 3. So -2, 5 pi over 3 would be back there. And this angle right here, that reference angle would be pi over 3. Okay? Now that angle right there would be, I guess, 2 pi over 3. Okay? These distances away from the origin will be both 2. Okay? It's just one is, it always puts you in the diagonally opposite quadrant. Okay. Other questions? No question there? Okay, well, let's start talking about graphing. So you're going to probably want your little computer, Chromebook, because you're going to want to. We're going to do some playing around on Desmos and stuff. I have Desmos up there on the screen. See? So we're going to start talking about graphing in polar world, okay? We're gonna toy around with some of the calculus today, but we'll really get into that more heavily next week, okay? So normally speaking, when you're talking about polar graphs or polar equations, it'll be like where your equation is written, R is some function of theta. Okay? Now, just an example of what I mean by that. Like R equals 2 sine theta, or R equals 3 cosine of 2 theta. Just stuff like that, okay? But it could mean that R is a constant. It's not a function of theta. What would that mean if R was a constant, not of a function of theta? Like R equals 5. That's the most basic of all polar graphs. It's like a linear equation in polar coordinates, but this doesn't graph what we think of as a line. What does it mean if r equals 5? Well, let's think about that for a second. What does r represent? Okay? You're thinking radius, okay, and I'm okay with that. But for our purposes, I want you to think about r as the distance from the origin. Okay? R is the distance from the origin. So I'm saying r is 5. It doesn't matter what theta is. The distance from the origin is always 5. What's that going to graph? Circle. Okay, check it. Graph it. If you haven't already. Oh, you probably know how to do this in Desmos. Have you done this before? In the Desmos, for grid, you can click the polar grid. Okay, and then just type r equals 5 over here and it'll graph the circle. Okay? So r equals 5 graphs a circle. Okay? But more importantly, it graphs a circle centered at the origin. Because r represents the distance from the origin, right? So when we think about a polar graph, okay, when we think about a polar graph, now that's just a random sketch, okay? What we're talking about here is the distance that each point is away from the origin is a function of theta. Okay? So for example, when theta is right here, we're that distance away. But when theta is right there, the distance is different. Okay? This is going to help me to know if you understand what I just said. So looking at that picture, okay? Looking at that picture that I just drew, for what value of theta is r going to be, does r appear to be maximum? And when I say for what value of theta, just give me a quadrant. For what value of theta is r going to be a maximum? And I just want a quadrant. I heard some people say 3. I'm hearing first, too. Okay? So, who said 3? Make a case. Do you want this? And I don't know this.
So I'm like, yeah.
It's definitely a bad bar.
But like compared to like, I guess like it just depends how you look at it. 'Cause, you know, that's pretty big.
Right, I could have probably drawn something more obvious, but I wasn't planning on asking you that question. But yeah, but you guys get the idea, okay? He looked for the place where this graph was furthest away from the origin. Okay. Now Savannah said 1. I mean, this could be just as big as that. We didn't get a measuring stick out. Okay. Beautiful. Okay. So now these graphs can do some wonky things. Okay. So the first one that we're going to do together here is r equals 4 cosine, and then to get theta, just type theta. Okay, so that's a circle. Agreed? What's the radius of that circle appear to be? The radius appears to be 2. And I would agree with that. What's the diameter then? 4. Okay? Now, I will tell you that if we don't shift graphs in polar like we do in Cartesian. Like, because if you think about this, I mean, we just talked about r equals 5, right? Like, you don't need to do this, but if I were to graph r equals 5 along with this, okay? What happened? I mean, you could say, well, that got smaller and we shifted the center over. Okay, but the shifting of graphs, like we're used to shifting of graphs, doesn't happen in polar. Okay, like horizontal and vertical stretches, you know what I'm talking about, right? So, how is this a circle? Okay, well, first of all, we know that r is not constant there. Do you agree with me with that? Like, remember, r is the distance from the origin. So if I look at, say, when theta equals 0, what's r? When theta equals 0, what's r? Well, you got two ways of doing that. You can look at the graph, or you can just plug it in. I'd probably just rather plug it in. Okay, the cosine of 0 is 1, so 0, 4. So when theta equals 0, we're right here. Okay? Now let's increase theta a little bit. How about when theta equals pi over 3? What's r? Well, let's just use the computer to calculate that. You happy with that? So we can just do r of pi over 3. Does that not work? Shut the front door. Oh, I just lost a lot of respect for that. How's that work? Oh, well, we'll have to do it old school. 4 cosine of pi over 3. We also could just do this by using special angles. So 2. So when theta equals pi over 3, what's r? It's 2. Okay, now let's look at this. Let's sort of do the analysis here. Pi over 3 is right here, right? So right here was theta equals 0. As I increase theta, right, what happened to r between here and there? Because that right there is the point 2 comma pi over 3, right? That angle is pi over 3. What happened to r? It got smaller. Okay, it got smaller. R decreased. The distance from the origin, as I moved from 0 to pi over 3, the distance from the origin went to 0, or got smaller. Okay? What is r at pi over 2? Zero. R at pi over 2 is 0 because the cosine of pi over 2 is 0. So notice right here, if I sweep theta from here to pi over 2, we're back at the origin. Okay, the radius is 0. The distance that the curve is away from the origin at theta equals pi over 2, the distance is 0. Okay? Let's do another one. Let's do 2 pi over 3. What's r when theta is 2 pi over 3? That should be easy. I didn't mean for it to be a trick question. Was it a trick question? Why do you think it's 0? I love that you say that, Megan. Okay? Even though it's not correct, I love that you say that because this is gonna be you're gonna make a connection. Megan's looking over here and she's like, hey, the graph isn't over there. So R must be 0. Okay? Which is a common thing because you're so used to thinking in Cartesian world, right? But if you do the math, which I think everybody that told me -2, they did the calculation right here. They didn't look at the graph. They looked at this and said, oh, it's -2, right? What does that mean? The graph at 2 pi over 3 here's 2 pi over 3, right? Here's the angle 2 pi over 3. R is negative, which means the graph is going to be in the opposite quadrant. So this point right here is the point -2, 2 pi over 3. Because R was negative. The angle put me in the second quadrant, but the negative R puts me in the fourth. Okay? And then what happens when we get to pi? Oh, sorry, we're not at 0, we're at -2. We're -4. When we get to pi, we're at -4. So, same idea. Look right here, the graph's not over here. At pi, which is right here, right? Here's pi. The graph's not over there. But the calculation says R is -4. That puts me back here. Okay? I made one complete circle, but I only made theta go from 0 to pi. Okay? In fact, you can't see this on Desmos. This is another chink in Desmos' armor. If I go and change this to 2 pi, what do you notice? When I made theta go from 0 to pi, I went around the circle once. When I made it go from 0 to 2 pi, what do you see? Did anything change? The look of that graph is exactly the same. But what actually happened is that you trace that circle twice. Right? You just can't see that. In the old TI calculators, when it graphed in polar, you actually could see it tracing over itself. Yeah, that was kind of a nice thing. Okay? Now, why does that happen? Well, we'll come back to that. We'll come back. Questions so far? Okay. Maybe we should algebraically prove that this is a circle that we know and love. Okay? In fact, could anybody just look at this circle and tell me the Cartesian equations of that circle? You remember how to do that? Did you take the ACT? This is on the ACT. Like center origin, or center radius. What's the center of that circle? 2, 0. So the equation of the circle would be this, right? Everybody agree with that? Can we algebraically prove that by converting R equals 4 cosine theta to Cartesian? Let's do it. Might as well knock this out real fast. Going to convert that equation to Cartesian. So do you guys remember how to convert? Our things were x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and theta was inverse tangent of y over x. Weren't those our equations that we converted with? Boy, that's annoying because I can't just straight up convert it, can I? I can't just make a substitution and switch it. So I gotta do something fancy. Anybody know what you gotta do? Anybody remember this? I'm not sure if you did this. It's hard to know what you did because you might have been looking at your basement. Or in your bedroom. I want to say, if I multiply both sides of this by r, what does that do for me? What's the left side now equal to? X squared plus y squared. And what's the right side equal to? Four x. Because r cosine beta is equal to x. So x squared plus y squared equals 4x. Is this equal to that? You disagree with that? Yep, for sure. Well, we'll just prove it real fast. We have to do something called complete the square. So, completing the square is basically turning a quadratic that doesn't factor into a perfect square. It takes a quadratic that doesn't factor and turns it into a perfect square. That's what completing the square is. Right? And everybody gets all, what's that expression, get your panties in a bunch? Everybody gets all about completing the square. And I think it's really because you don't really know why you do it and what it's for. Like, the actual technique of completing the square really is not that hard. But you just get all jacked up because the algebra even gets a little bit complex, and I don't think you understand why you're doing it. So we're gonna turn x squared minus 4x into a perfect square. That's what we're gonna do. Okay? So I've got to add something to this to make it a perfect square, right? Now y squared is already a perfect square, right? Isn't it already y minus 0 squared? And I got 0 on this side. So what do I need to add to this right here to make it a perfect square? Okay? Well, if you're not sure, the way you figure it out is you look at this number right here, and you take half of it, which is 2, and then square it. What's 2 squared? 4. So I'm going to add that 4 there. But if I add it here, I have to add it to the other side because this is an equation. And you can't just go willy-nilly adding things to one side and not do it to both sides. You got to maintain balance in your life, right? So that's 4. Now, this factors by design. Like you made it factor. It factors into x minus 2 squared plus y squared equals 4. Okay? So it is a circle. All right? It is a circle. Okay. Let's do another one. Let's look at r r equals 3 sine of 2 theta. Okay, so one thing, what do you notice about this graph right away? One thing you notice. There's no wrong answer here. What's one thing you notice?
Not a circle.
Not a circle. What else do you notice?
All the quadrants.
It's in all 4 quadrants. Okay, it's in all 4 quadrants. And this window for theta was 0 to 2 pi. Okay? It's in all 4 quadrants, right? So if you were to describe for me what's happening, like if we were to kind of make a chart like we did a second ago, theta, r. If I start at 0, what's r? 0. Okay? Now, describe for me what's happening to r as theta increases now. It gets bigger, and then what happens? It gets smaller and goes back to 0. Then well, we don't know, but we do know that it gets bigger and then smaller, right? So, like, in fact, when is it the biggest? Okay, well, we can figure that out in a minute, okay? Don't know the answer to that just yet. Megan says it looks like it's a pi over 4. Okay, because she's kind of just reading it off the picture, which is fine. But we can actually prove it in a minute. All right, so this is what I want you to do for me right now. I want you to change this and change this so that you only graph that first pedal. Did you do it? Did you know how to do that? How did you do that? Okay, so you all just put pi over 2. So then that's how you concluded that it was halfway, and pi over 4 is where the max was. Okay, so then can you algebraically prove to me that that's pi over 2? How would you do that? How would you algebraically prove that that's pi over 2, where it starts out and then stops back and goes to 0? How would you prove that algebraically? Set r equal to 0. So 0 equals 3 sine 2 theta. So 0 equals, where's the sine equal to 0? So 2 theta equals 0, pi, 2 pi, 3 pi, etc. So theta is 0, pi over 2, 2 pi over 2, 3 pi over 2, etc. Okay. But now, you all told me pi over 2, so I'm going to put pi over 2 here. That's what we wanted. But then when we were talking about describing the behavior of the graph a minute ago, I heard some varying answers. Because we said, oh, the graph r increases, and then it goes back to 0, and then what? So what happens when we go between, say, pi over 2 and pi? Is that going to make a pedal? We think it would. Where's that pedal going to be?
fourth quadrant.
E over 2. Oh, so wait a minute. So now describe for me what's happening to the R as we increase theta from pi over 2 to pi. What's happening to R? R is getting more negative and then going back to 0. Okay? R is actually decreasing, but it's negative. Okay? Then what happens when we go from pi to 3 pi over 2? What happens when we go from pi to 3 pi over 2? Now we're back in the fourth quadrant. So now R becomes positive again, and then it increases and then decreases back to 0. Right? And then the last chunk is going to be almost exactly like the chunk we just looked at, right? As we go from 3 pi over 2 down here to 2 pi right there, we're going to get that last pedal, but it's going to be in the second quadrant. So we know all that time R is negative. So R is getting more negative and then comes back to 0. So R decreases and then it increases back to 0. Okay, does that make sense? So can we tie this to calculus? Okay, so here's my question for you. What time do we get out of here? That wasn't my question. Okay, so here's my question for you. Math erases. Look at that. Erases very nice. What was our equation? R equals 3 sine of 2 theta. What's dr d theta? It's a derivative, but just go ahead and find it, because I think you guys can find it easier than you can explain it. I want to be able to explain it. You get that? I hope. Did I do it wrong? No, I'll do it right. You guys just didn't look at me very confidently. I started getting a little nervous. Maybe you guys were just fancy pants and did this. You ready for my question? Before you compute this, before you compute the answer to this, I want you to tell me what its sign will be based off of the discussion that we were just having. Where's 2 pi over 3? It's in the second quadrant, yeah? Okay. So I'm going to go from pi over 2 to pi. what's going to be the sign of that derivative based off of our understanding of what that graph is doing. So maybe we need to review something from first semester. If dr d theta is positive, r would be getting bigger as theta gets bigger. R would be increasing. If dr d theta is negative, then r would be decreasing as theta increases. So when I'm at 2 pi over 3, okay, we're there. At that moment, is r increasing or decreasing? So it's decreasing, you're telling me it's getting more negative. What? Oh. R is getting more negative? So here we are at pi over 2 was here, right? And then as we increase from pi over 2 to pi, we were doing this, right? The R's were getting more negative, and then they're super negative, then they start increasing back to 0. Okay? So I can tell you that this is going to be negative because I understand how that's graphing. Okay? Now check it. Is 6 cosine of 2 times 2 pi over 3, is that going to be a negative number? Megan's going to check it real fast. What? Negative 3, yeah. Because that was 1/2. Okay? So I'm going to put some problems in the Google for you. This is going to be some converting. You won't be asking derivative questions because I wanted to keep talking about that. And then Monday we'll start talking about area. Are you planning on putting these problems right after next period? All right. I like to put them in beforehand, but sometimes I just don't know what's going to happen in class. I have an idea, but I knew what I wanted to do there.
Did you know that we were gonna prove it?
Yes, that was but I didn't know, I wasn't sure if I was going to get here.
Oh, I was gonna look it up my status tonight, and I can let you know. I have a full too.
Well, yes, congratulations. Where's yours?
In my bag, it's just broken.
You broke it?
I didn't like carrying it
You know you get
around.
kicked out.
No. I know.
Who did? Hey, you too. See ya. Any chance? I can use it to get it. So, in 6th grade, I broke my ankle. And tendon in my ankle that holds it together pretty much.
They didn't look good into it. Actually,
Just found out yesterday.
she got one. She got one.
surgery might be.
There's so many
Holding
people
my
that get
ankle bone backwards.
the one up there, right, too.
Yeah, it connects like your foot to your ankle.
Actually,
So he tried to move this foot, it didn't move. This one, it moved. I'm just gonna hold up, you know, to track people. Yeah, just stretch. But he doesn't want like the train stretch. He doesn't want to do anything and like have tape on it. It will not like this, like more tape. Like he tape, yeah. Or which, yeah, so. Is awful. There's like the laces. They're like really long, so I like tuck them in. And then with the laces, after the laces, there's a strap here that goes down and across and up. Like a strap here that goes down and across and up. And then there's a strap back here that goes across. Like it is. What do you mean by like this? It's awful.
You know,
That's
hey. You know Julie was not happy. Oh, I knew that. That's what you did.
yeah.
congratulations on the success. I saw your flyer yesterday.
Yeah, every day.
You just took the notes. I tried to get there and 32. Yeah, because when I get back to Canada for, but I know, and yeah, over there.
They gave you
It's like, literally like, that, like, this is huge fire.
literally so good.
Yeah, and like, Joe just threw them, like, you know, like the automatic that like comes up, he just threw them all of it. The last time I went there, this is what I noticed that I was there.
You're crash your car.
But not like.
You're not gonna starve to death.
Yeah, I mean, if you're not able to.
Literally, what are you coming back to practice?
Because they did it last time. The way they were doing it.
You don't know. I'm not. You are. No. I stopped doing stress. The doctor disappointed in me. Wait, you told you. We didn't tell us like what was wrong with you. I knew that something was wrong with you, but what did he was just like really not. I mean, yeah, he said you're out for like a couple of months.
Problem solved, baby. Look at that.
Yeah, the doctor said I can't run for a month, and then I have to start PT the next month.
You can't run for a month. You drink this?
I drink it.
I probably will. If I have to.
Well, if you had to, so.
Well, I mean, I was dying first.
If you were gonna give me.
Or if you were gonna make it, say, I'll give you $5 a drink.
Yeah.
Oh.
I do.
Would you give me $5? Are you sure?
So let's talk about graphing and polar world. Well, any questions on the homework? Est-ce que vous avez des questions avec vos devoirs? Non? C'est magnifique. Well, if that is the case, then let's start talking graphing. Why not, man? So you will need your Desmos machines at some point. If you want to grab those, you can. No. So my emphasis on this or with you today, like you guys have all had some experience in graphing and polar coordinates, okay? But it's one thing to just like graph these equations and say, oh look, this is a star. Oh look, this is a flower. Oh look, this looks like a butt. Like, we want to be able to do a little analysis with these things, like to understand why the graphs are doing what they're doing, because that'll help us do the calculus. And we're also going to probably use some calculus to help us understand why these graphs are doing what they're doing. Okay? So all kind of connected. So when we're talking about graphing and polar coordinates, by the way, Billy, Gavin, where'd this one come from? Well, I've been really enjoying using it. It really writes nicely on the board. I just walked in here without yesterday afternoon. It was sitting out there.
That's because I wrote on the board the other day.
So, all right. Anyway, so when we're in graphing and polar coordinates, typically we're talking where r is some function of theta. Okay. Now, when we're talking about r in a graph or in polar coordinates, what is r representing? What is r representing? Okay, so you say radius, which that's what everybody says initially, but I want to dig it a little deeper than that. Hello? Yeah. Yeah. Okay. I'll have to text Amber and ask her. My kids, I would say, I only have two that I think had signed up originally. I can text Amber after this period, or I'll just call her and ask her what she's thinking, what she would want. So she gains a week. Okay, let me call her and then I'll check back with you like after lunch sometime. Okay, thanks. Bye. What were we talking about? R, radius. Okay. So radius, yeah, I like radius, but I want us to think a little bit bigger than that. Because when we think radius, we're automatically thinking circle. But We could think that. But let's think of r as just the distance from the origin. Isn't that what r is? R is the distance from the origin. So the most basic of graphs, well, before I get to that, so when we graph polar equations, we're saying the distance that this graph is from the origin is a function of theta. It's changing as theta changes. Okay? The most basic of polar graphs is if r doesn't change. Right? R equals 5. What would that be? If I said, hey, it doesn't matter what theta is, r is always 5. The distance is always 5. What's that going to be? Circle. Okay? More importantly, it's going to be a circle centered at the origin. Okay, because as you're going to see in a second, we can have circles that don't have equations r equals 5. All right? But r doesn't change. It's constant. Okay? All right, well, speaking of circles, let's look at another one. So how about this one? R equals 4 cosine of theta. R equals 4 cosine of theta. Okay? So go ahead on your Desmos, if you have a Desmos. Go ahead and graph that. Okay? First thing you might want to do is go to the wrench and change the grid to a polar grid. That's kind of nice. All right? And then type R equals 4 cosine. And theta, it's actually easier just to type the word theta. Does everybody got a circle? So this circle, what is the radius of that circle appear to be? What's the radius of that appear to be? Okay, what did you say? 2? Okay, what's the diameter? 4? Okay? Now, if you notice, the equation of this circle and the equation of the other circle are vastly different. Okay? So one of the things that we sort of need to get straight in our heads is that transforming graphs, like shifting, stretching, shrinking, like you're used to with graphs, that does not work the way it traditionally works in the world we've been living in. Okay? You can't think of this circle necessarily as a shift to the right 2 and a compression of the other one. Like, there's not an easy algebraic explanation to that. You follow what I'm saying? Okay. So if I were to make a table for this circle here, and I were to look at what this graph is doing, because I want to be able to describe this graph and understand why this graph looks the way it does. Okay? When theta equals 0, what's r? When theta equals 0, what's r? Now that shouldn't be difficult. You should be able to just do that in your head. The cosine of 0 is 1. And 4 times 1 is 4. So when theta equals 0, r is 4. Okay? So right here, when theta equals 0, r is 4. Boom. Okay? So when theta equals 0, the distance that this graph is away from the origin is 4. Okay? What about when theta equals pi over 3? What's on? What's the cosine of pi over 3? 1/2 times 4. So when theta equals pi over 3, r is 2. Okay? So some of you might have just picked that off the graph because you went to pi over 3. You said, oh, what's that distance right there? It's 2. Okay? Question?
Is there a reference to put in points and?
No, it's annoying. It's really annoying. Now, what you could do is make the table that we're making, you could generate that, but you'd have to create another line that you call it y equals. Okay? But you can't just. I tried doing r of pi over 3 last period, and I couldn't do it. I was real tedious. Okay. So now let's look at this graph for a second, kids. As theta increased, or as theta changed from 0 to pi over 3, what happened to r? It got smaller. As we moved theta out, those r values got smaller. Okay? The r decreased. Okay? In fact, if I were to ask you to calculate this, okay? If I were to ask you to calculate that, we could compute it, and we will, but you should be able to tell me the sign of that quantity without doing any work at all. You should be able to tell me whether dr d theta would be positive or negative without doing the computation, because we just answered it. Now, it's interesting that I would wager right now, most of you would feel more comfortable just computing the answer to that than explaining to me whether it's positive or negative and why, without doing the computation. So if dr d theta is positive, what does that mean? It means as theta increases, r increases. If dr d theta is negative, it means as theta increases, r decreases. So at that moment, when theta equals pi over 3, what's happening to r? What's happening to r, Mia? It's getting smaller. Okay? We saw that. And it's big here, smaller, 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 smaller. So whatever the answer to that is, we know it's going to be negative. Okay? Now we could go ahead and compute it. Well, what's dr d theta? It's negative 4 sine theta. So evaluate that when theta equals pi over 3. And that's negative 4 sine of pi over 3. So that's negative 4 times radical 3 over 2. It's negative. Okay? Okay. What's r when theta is pi over 2? What's r when theta is pi over 2? What's r when theta is pi over 2? Devin, what do you think?
0.
0. Did you plug in pi over 2 there?
Yeah.
Okay. What's R when theta equals 2 pi over 3? Now I'm hoping that if you're trying to do this, if you're looking at this graphically, I'm hoping something went off. Something got triggered in your mind. Like, wait a minute. Because if theta equals 2 pi over 3, where's the graph? It's not there. What's R? Is it 0 then? What is it? It's -2. If theta equals 2 pi over 3, if we actually plugged in 2 pi over 3, we're going to get -2 there. R is -2. So here's 2 pi over 3. So we're at -2, which means we're right there. Okay? And then what's happening to R as theta goes from pi over 2 to pi? What's happening to R? As we go from pi over 2, when we're at 0, then what happens to R? As we sweep theta out, what's happening to those R values? They're increasing, they're getting bigger. Okay? And then when we get back to pi, what's R? Back to +4 again. Sorry, it's -4. But hold on a second. Mia, you told me that R is getting bigger as I increase theta from pi over 2 to pi. As I go from here to here, R is getting bigger.
Mm-hmm.
I'm not sure that I agree with that. The distance is getting bigger. And I sort of led you to say that, so that was my fault. The distance is getting bigger, but what's actually happening to R? It's getting what? It's decreasing. Because why? How is the distance getting bigger, but it's decreasing? It's getting more negative. Yeah. I knew you knew it. I had to get it out of you. Okay? Somewhere in there, though, it switches to increasing because it's getting less negative. In fact, it's right out here. Okay? Then, as soon as we get past here, now, oh no, I guess it's not. It's decreasing the whole time. We have this length right here is bigger than that length right there. So let me ask you this. If I were to ask you the sign of this, what would it be? Without computing it, we can compute it. What's the sign of that going to be? Is R increasing or decreasing when theta equals 2 pi over 3? Is R Okay? It's decreasing. It's getting more negative. Okay? So maybe when we're talking about R, we should really be saying that R isn't the distance, the absolute value of R is the distance, right? Because when R is negative, the distance, like, when R is negative 2, the distance is 2, but R is negative 2. Okay? So notice that the bounds for theta here were 0 to pi. What would happen if I made it 0 to 2 pi? Yeah? Did the graph change? The graph itself didn't change. But what actually happened that we just can't see? It just went and plotted it right on top of itself. This is another downside of Desmos. In the old TI calculators, when you graphed in polar, you could actually see it tracing back over itself. Okay? You don't see that in Desmos. So you're saying that's a circle, right? Can you prove to me that's a circle? Can we prove that's a circle algebraically by converting this equation to Cartesian? R equals 4 cosine of theta. Can I convert this to xy? Sure. So the equation of a circle, if you remember, took the ACT. I think that's on the ACT. What goes inside the parentheses? That wasn't on the ACT this year? I've seen it on the ACT before. What goes inside those parentheses? What? H and K? Well, yeah, but what are H and K? The center, right? HK. So if it's at the origin, it's just x squared plus y squared equals r squared. Okay. What's the center of this circle? 2, 0. So apparently this circle then has to have this equation, x minus 2 squared plus y squared equals, and what's the radius of that thing? 2. So r squared would be 4. So apparently this and that are equivalent. And you're just going to believe that. And you prove it. Can you prove that using the conversions like, oh, we know x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and theta is the inverse tangent of y over x. Didn't we talk about that yesterday? Yeah. Okay. So can you use those 4 pieces of information to turn this into this? So how can we turn that into that? doesn't really, I can't just make an automatic substitution, can I? It'd be really nice if that were 4r cosine. What would that equal? It would equal 4x, right? Well, let's make it that way. Multiply both sides by r. Is that legal? Can I just multiply both sides by r when I have an equation? Absolutely. Oh, but wait. R squared equals x squared plus y squared. And r cosine theta equals x. So x squared plus y squared equals 4x. Is that equal to that? Does x squared plus y squared equal 4x? Does that equal x minus 2 quantity squared plus y squared equal 4? You're just going to say, yeah, it does. I mean, it has to get better. Otherwise, we really screwed up. Yeah, it does. Watch. See? It equals that. Hold the phone here. I need to turn that into a perfect square. I need to factor that into a perfect square. And you say, wait, it's not a perfect square. But you can make it a perfect square. Because you can do something called complete the square. You ever heard of that? Completing the square? Yeah, you ever heard of completing the square? Yeah. You remember how to do it? It's one of those things like when you ask kids to complete the square, it's like asking them to clean the bathroom. Like they just groan. Like they think it's like they're shoveling up horse manure or something. The problem with completing the square is you don't know why you do it. You just do it because someone told you, and then you fill out a worksheet and you do 100 of them. Right? Why do you complete the square? What's the purpose of completing the square? It's to make a quadratic that is not factorable a perfect square. This isn't a perfect square right now. Okay, so let's make it a perfect square. So I'm going to add something to it to make it a perfect square. But if I add it to that, I got to add it to that side. Because it's an equation. You got to maintain balance in your life, people. What do I have to add to this to make a perfect square? Now, if you don't know, if you can't just see it right off the top of your head, there's a way to figure it out. You look at this number right here, and you take half of it. And then you square it. So half of -4 is -2. Squared is 4. So I put a 4 there, and then I put a 4 there. Now I've got a perfect square. I'm going to factor this. How do I factor that? Oh, it's x minus 2 squared. How do I know that? Because I designed it to be. I made it x minus 2 squared. Oh, look at that. It worked out the way we thought it would. Okay? What? Sorry, guys. It's not that hard. I mean, I would rather do that 10 times than clean a bathroom, especially a public bathroom. Okay? All right, let's look at another graph. So we got to be able to convert those things back and forth. Let's look at a more fancy pants graph. So let's look at this graph. R equals cosine of 2 theta. R equals 4 sine of 2 theta. I love how you just type it. We gotta figure out why this graph does what it does. So when theta equals 0, what's R? The who? Actually, before we get too carried away here, when you look at that graph, what do you notice? What are some things you notice about that graph? I mean, there's no wrong answer. Nicole, what do you notice? What? Huh? Yeah, what do you notice with the graph? It looks like a flower. Okay, I agree. It's called a polar rose. What else do you notice? None of you notice anything? You have no observations whatsoever? There's 4 petals?
Yeah.
Okay, what else?
It's not a function of y or x. I mean, you want to write it in terms of function of y, in terms of y and x.
I'm not sure what you mean by that.
Like if you were trying to write it in, like normal system, we have to have a function in terms of y and x because it has to have the horizontal order for one side.
Oh, okay. I see. I get it. What else?
I'm going maximum distance and the origin to the outside of petals is 4.
So you're telling me R's max is 4? Okay. Did you just count that on the graph? Like you count it out?
Both play around with the equation, then you kind of change the 4 to like 5, then it's going out to 5.
Yeah. What else do we notice? The first thing I noticed about this one compared to the last one is it's in all 4 quadrants. Okay? All right, so what's theta, when theta equals 0, what's R? 0? We already said that? When theta equals pi over 2, what's R? It's also 0. 4 sine of pi would be 0. So explain to me then what's happening to R as theta goes from 0 to pi over 2? What's happening to R? The distance increases and then it decreases, right? And since between 0 and pi over 2, the graph is in the first quadrant, we can actually say R increases and then decreases. Okay? And in fact, if you change this number right here to pi over 2, that's 0 to 2 pi, make it go 0 to pi over 2 instead, you just get that first petal. Okay? So R increases, okay? And then it decreases. In fact, Gavin's right. The max that R happened is right there. And it was at 2. And that's where R changed from increasing to decreasing. You see that? R changed from increasing, and then it's decreasing. Okay. Now, what about if we increase theta from pi over 2 to pi? Okay, both of those values are 0, but what happens in between there? Okay, what happens in between there? Where's the graph? Figure it out. Change the bounds on your graph. Make it go from pi over 2 to pi.
Make it go from pi over 2 to pi. Billy, what are you doing? Look, I made a spiral.
Well, you made all kinds of pretty pictures.
Look, it's a spiral.
So from pi over 2 to pi, where's the graph, Mia? It's in the fourth quadrant. But isn't pi over 2 and pi in the second quadrant? Yes? So what's happening to r then? Or what does r must be during pi over 2 to pi? What does r have to be? Very good, negative. Okay, so now, hold the phone. Hold the phone then, friends. Whoa! I overdue. Okay. This is going to tell me if you understand how polar graphing works. Are you ready? Find for me this. Actually, just the sign of this. Without computing it. Without computing dr d theta, that theta equals 2 pi over 3. Tell me what the sign of it has to be. Based off of what's going on with this graph. Because as I increase theta from pi over 2 to pi, this graph goes like this. I'll put an arrow on there indicating the direction. So if you can tell me the sign of this, you understand how polar graphing works. If you can't tell me the sign of that, then we've got some more work to do. And you can tell me the sign of it without computing it. Who thinks they can do it? Mia does, Gavin does, Samuel does. Billy, can you? No. Well, that's because you were drawing spirals. Jimmy speaks. Jimmy, what do you think the sign is? At 2 pi over 3?
Oh,
2 pi over 3 is right here.
so
So we're down here. So what's the sign going to be?
negative,
Why?
because it's becoming more negative. Like if it was,
Because r is decreasing, becoming more negative. Right. I mean, that's all you had to say. Perfect. Right? And then right here, say at, if I did dr d theta at, well, go ahead and compute it. So what is dr d theta? It's 4 cosine of 2 theta times 2, or 8 cosine 2 theta. So you can plug 2 pi over 3 into that. So that's going to be 8 cosine of 6 pi over 3, or 2 pi. Wait a minute, something. 4 pi over 3. Yeah, 4 pi over 3. Miller can't do that. And what's the cosine of 4 pi over 3? So there you go. It's going to be negative. All right, what would the sign of this be? What would the sign of that be? Samuel? You think? I think it's positive. The 5, 5, or 6 is right here, which means we're down here, right? R is actually increasing here because it's getting less negative. Okay? Check on the Google. I'm going to post an assignment here. It's not going to deal with derivatives. It's going to deal with converting and just making some graphs. Yeah. And have a splendid weekend. Filled with lots of joy. Yeah, I don't think you can. If you can. Yeah, give you like each half.
Yeah. It's only in tax.